Every day, industries make decisions whether to invest in a product, allocate resources, or schedule production. Many of these decisions involve yes or no choices, which are typically modeled using binary variables in optimization problems. In most cases, we assume relationships are linear, but real-world scenarios are often more complex. This is where quadratic programming comes in. Quadratic programming helps model applications like portfolio optimization and budget allocation, where decisions are not just linear but quadratic, meaning variables interact in ways that makes the problem harder to solve. However, these problems become even more challenging due to non-convexity and integer constraints. A common approach is to convert them into mixed integer programming or semi-definite programming problems, but there is a trade-off. Mixed integer programming struggles with efficiency, and semi-definite programming, though powerful, it is computationally expensive. This is where second-order cone programming provides a breakthrough. It offers a scalable, computationally efficient alternative for solving binary quadratic programming problems. My research introduces a hierarchical SOCP framework that progressively refines relaxations, leading to a stronger solutions with lower computation effort compared to traditional methods. Along with this framework, we have developed a scope algorithm where we enhance branch and bound algorithm using SOCP relaxations by reducing computation time, improving solution quality, and making it possible to solve large-scale 0-1 quadratic programming problems effectively. Beyond theoretical advancements, my research also applies second-order cone programming to batch scheduling problems, which are critical in industries like pharmaceuticals, chemicals, and food production. Manufacturers need to decide what to produce, when and in what order, all while minimizing cost and optimizing resources. Traditional scheduling methods struggle with large-scale problems, but by integrating SOCP-based constructs, we can generate better schedules faster and improve overall efficiency. By advancing SOCP-based optimization techniques, my research helps solve complex QP problems in finance, engineering, and manufacturing. Ultimately, this work bridges a gap between theory and real-world decision making, making industries smarter, faster, and more efficient.